What if zooming in didn't reveal something new, but instead revealed the same shape again? When we look closely at the world around us, we notice patterns. But what's surprising is that those patterns don't disappear when we zoom in or out. In many cases, the shape stays the same, even as the scale changes. For example, look at this broccoli. Each branch looks like a smaller version of the entire plant. And when you zoom in further, the same pattern repeats. Now look at these tree branches. Notice how large branches split into smaller ones, and when we zoom in, those smaller branches split again, creating a pattern that looks similar at every scale. Even at a much smaller scale, the leaves show the same branching pattern in their veins, whether we look at the whole leaf or when we zoom in close. This type of pattern is called a fractal. One of my favorite formal definitions comes from the Cambridge Dictionary, defining it as a complicated pattern in mathematics built from repeated shapes that become smaller and smaller or larger and larger each time they are repeated, so that the pattern appears the same at whatever scale it is seen. A classic example is Romanesco broccoli. Zoom in and you see a smaller copy of the same pattern. Zoom in again, same thing. It's like each little bump is a mini version of the whole vegetable. Fractals appear just about anywhere, and we can find them in the most random places. For example, that branching pattern we saw earlier in trees also appears in lightning, blood vessels, lungs, rivers, and much more, all following a fractal pattern. So why does nature keep using the same pattern of fractals over and over again? What is so special about fractals that they exist in abundance and in completely different things? The answer lies in efficiency. Fractals are the most efficient way to spread out, fill space, and move energy. For example, this branching pattern in rivers allows them to distribute water efficiently across a large area, minimizing energy use. This pattern is also the most efficient way to drain a landscape. The water repeatedly follows and deepens the easiest downhill paths at all scales, creating self-similar branching patterns through erosion over time. Lightning also follows a branching pattern because electricity always seeks the path of least resistance. As it moves through the air, it repeatedly splits into smaller paths, creating the same fractal pattern we see throughout nature. When it comes to trees, to absorb maximum sunlight, they need to spread out and increase their surface area as much as possible. More surface area allows the trees to absorb more sunlight, and this fractal pattern allows trees to greatly increase their surface area while barely increasing their volume, minimizing their use of energy and resources. Lungs spread air across your body. This branching pattern allows our lungs to have an incredibly large surface area without taking up too much space inside our body. In fact, due to the millions of tiny air sacs in our lungs, known as alveoli, the surface area of our lungs is about half the size of a tennis court. More surface area means more oxygen can enter the blood and more carbon dioxide can leave. Blood vessels use the same efficient design. By branching again and again, they create a huge surface area worth several tennis courts inside a small space, making it easy to deliver oxygen and nutrients to every cell while using as little energy as possible. Neurons branch to maximize both surface area and the number of connections they can make, allowing information to travel quickly and efficiently while using minimal space and energy. The placenta uses a similar branching design to increase surface area without increasing volume, maximizing the exchange of oxygen and nutrients between the mother and the baby. A Koch snowflake is a great way to show the same idea, just on a 2D scale. These are the stages of a Koch snowflake. You start with an equilateral triangle, divide each side into 3 equal parts, add a smaller equilateral triangle in the middle, and then repeat the process over and over again. With each step, the area only increases slightly, whereas its perimeter, the length around it, increases significantly. In fact, its area will approach a finite number, whereas if you continue this process forever, its perimeter would approach infinity. The reason the area approaches a finite number is because the shape will never have a larger area than the shape that surrounds it. For example, even though the pattern keeps repeating, the snowflake will never grow beyond this boundary. So its area only increases up to a certain point. But the perimeter will grow to infinity because each step adds more and more sides. Just as each step of the Koch snowflake dramatically increases the perimeter without adding much area, systems like lungs, trees, blood vessels, neurons, the placenta, and much more use fractal branching to increase their surface area while barely increasing volume in order to maximize efficiency. The Koch snowflake is also a great example showing how simple steps can form complex shapes. You are essentially just adding another triangle to each side over and over again, starting out as a simple equilateral triangle and becoming more and more complex with each step. An example of this in real life is coastlines. Let's try to measure the west coastline of Norway. How would we do it accurately? Would we measure this line? Well, what if we zoom in? Now we have all these inlets, bays, and ridges that we didn't account for in our last measurement, which if we account for all of these will give us a much longer coastline. What if we zoom in again? Now we have even more inlets, ridges, and bays that we didn't measure on the previous map, making our coastline even longer than our last measurement. The answer to how long a coastline is depends on how closely you zoom in. Just like with each step of a Koch snowflake, every time you zoom in on a coast, you discover more bumps, more curves, more details, increasing the length of that coastline, like how the perimeter of the Koch snowflake increases with each step. Like a Koch snowflake, coastlines are fractals as well. Okay, so we see the same patterns in broccoli, trees, lungs, rivers, blood vessels, lightning, coastlines, and even abstract mathematical shapes because this is nature's way of increasing efficiency. With just a few simple rules repeated across different scales, the universe builds complex structures capable of moving air, water, energy, and life itself, all while using the least amount of resources possible. From the smallest veins in a leaf to the edges of our continents, similar patterns emerge again and again. And once you start noticing them, you can't help but see them everywhere. The small mirrors the large, and the universe feels connected. Hey everyone, this is Josh from Wise Owl Academy. Thank you so much for watching the video, and if you enjoyed it, feel free to leave a like and subscribe for more. We offer online math tutoring for students in grades K through 12, and we even offer a free trial class to see if it's a good fit. You can sign up on our website, the link is in the description below. Hope to see you all there.